Hello everyone and welcome to another IB Physics video. Today we will be looking at a paper 2 exam from November 2020. And let's get started. In this first question it says, a company delivers packages to customers using a small unmanned aircraft. Rotating horizontal blades exert a force on the surrounding air. The air above the aircraft is initially stationary. The air is propelled vertically downwards with a speed of v. The aircraft hovers motionless above the ground. A package is suspended from the aircraft on a string. The mass of the aircraft is 0.95 kilograms, and the combined mass of the package and the string is 0.45 kilograms. The mass of air pushed downwards by the blades in 1 second is 1.7 kilograms. Part A, Roman numeral 1 of this question says, state the value of the resultant force on the aircraft when hovering. Well, this question states that the aircraft is motionless as it hovers. Velocity is 0 and it stays at 0. That means the acceleration is 0, and therefore the net force must also be 0. And of course, the resultant force is referring to the net force. In part 2, the question asks to outline, by reference to Newton's third law, how the upward lift force on the aircraft is achieved. Now, Newton's third law states for every force there's an equal and opposite force. So if you go back into the question, notice that it has a reference to a force, and it's the force of the horizontal blades on the air. So we will write that down. The blades exert a force downwards on the air. Now, we will use Newton's third law, which says, therefore, an equal and opposite force is exerted by the air on the blades. In part 3 of this question, it says determine v, the velocity of the air. State your answer to an appropriate number of significant figures. So, number 1, we know the mass of the aircraft. In fact, we know we have to use the total mass. So the total mass is the mass of the aircraft, which is 0.95 kilograms, plus the mass of the package and string, which is 0.45 kilograms, which would be 1.4 kilograms in total. So the gravitational force or the weight on the whole aircraft system would be mg, which is 1.4 times 9.81. Before we solve that, this downwards force is being counteracted by the lift force. So the force of lift is equal to mg. And finally, it's the air pushing the blades upwards. And we're going to use the impulse over time as the force by the air in pushing the blades of the aircraft upwards. So basically the force is equal to the rate of change of momentum. This would be the amount of mass of the air that passes through every second multiplied by the velocity. So here, the impulse or the change in momentum is the change in mass times the velocity. But the reason we write it like this is because the change in mass over time is a quantity that is given by the problem. The number of kilograms per second. This is 1.7 kilograms per second times the velocity of the air should equal to the mass of the whole system, which is 1.4 kilograms, times the gravitational acceleration of 9.81. This would give us that the velocity of the aircraft, or not the aircraft, the air going downwards would be about 8.1 meters per second. And we used two significant figures because most of the values of mass and the values for the number of kilograms per second are all in two significant figures. So the answer should be in two significant figures. In Roman numeral 4 of this question, it says, calculate the power transferred to the air by the aircraft. The power transferred to the air, well, initially the air doesn't have any energy. As the air passes through the blades, it is giving kinetic energy. So it would be the amount of kinetic energy you give to the air per unit time. That would be 1/2 the mass of the air times velocity squared over the change in time. And again, this value here is the number of kilograms passing through every second, mass over time. This is again 1.7 kilograms per second. So it's 1/2 times 1.7 kilograms per second times, and we already found the velocity of the air, 8.1 meters per second squared. And this would give us approximately 56 watts. There's another way to solve this question, but it's slightly, it's a little bit tricky. So what we want to do is take the power as being the force times the velocity. But here, remember, it's the average velocity. Because this velocity of 8.1 meters per second is not the same velocity as in the beginning. The air is not always the same velocity. To get the average, you have to get the final velocity minus the initial velocity divided by 2. We have the force, and we're talking about the total force on the system, which is the total mass times the gravitational acceleration multiplied by the final velocity is 8.1 meters per second, and the initial velocity is 0. You divide this by 2, and you get the power. Incidentally, it would still be 56 watts. You should get the same result. So be careful with this. The tricky part here is you're not supposed to use only the final velocity. You have to use the average velocity. In the next part of this question, part B, the question reads, the package and string are now released and fall to the ground. The lift force on the aircraft remains unchanged. Calculate the initial acceleration of the aircraft. First, we will find the net force on the aircraft. The lift force is still the same. And now you have to subtract the weight of the aircraft, or the gravitational force on the aircraft, now that it's not connected to the package. The original lift force was just enough to keep the aircraft hovering and to counteract the gravitational force of the aircraft and the package, which would be 1.4 times gravitational acceleration. And we will subtract the gravitational force on just the aircraft, which is 0.95 times gravitational acceleration. And this would be 0.45 times the gravitational acceleration. Incidentally, this is also the force on just the package. So because you cut the package out, the net force will be this much. Acceleration is the force over the mass. We have 0.45 times 9.81 for gravitational acceleration. Now, this mass here is just the mass of only the aircraft, which is 0.95. And this will give us an acceleration of 4.6 meters per second squared. On the next question, question number 2, the question reads, the rotor is an amusement park ride that can be modeled as a vertical cylinder of inner radius r, rotating about its axis. When the cylinder rotates sufficiently fast, the floor drops out and the passengers stay motionless against the inner surface of the cylinder. The diagram shows a person taking the motor ride. The floor of the rotor has been lowered away from the person. Part A says, draw and label the free body diagram for the person. First, we assume this is on Earth, so there will be a gravitational force downwards. You can label this W for weight, or force of gravity, Fg, or mg. Now, if there were only this one force, of course, the person would just slide down. Second, there is a force towards the center of the cylinder, which is how the person is able to maintain the horizontal circular path, like this. This force is provided by the normal force of the wall. Finally, if only these two forces were acting on this person will still slide down. There's a third force that counteracts the force of gravity. Of course, this is the force of friction. For part B, the question reads, the person must not slide down the wall. Show that the minimum angular velocity, omega, of the cylinder for this situation is omega is the square root of gravitational acceleration over the friction coefficient times the radius, where mu is the coefficient of static friction between the person and the cylinder. So, in order for this to occur, the force of friction must equal to the weight of the person. This weight is, of course, mass times gravitational acceleration, and the force of friction is the coefficient of static friction times the normal force. In this case, the normal force has to be the force that is required to keep the person moving in a circular path, which means that the normal force will equal to the centripetal force. In terms of angular velocity, this would be mass times angular velocity squared times the radius r. So let's substitute that. Friction coefficient times the mass times the angular velocity squared times the radius of the cylinder is equal to mg. Simplifying for omega, the angular velocity, you get omega is equal to the square root of gravitational acceleration divided by mu r. In part C, the coefficient of static friction between the person and the cylinder is 0.40. The radius of the cylinder is 3.5 meters. The cylinder makes 28 revolutions per minute. Deduce whether the person will slide down the inner surface of the cylinder. First things first, we will calculate the minimum angular velocity. And of course, this is just the same equation that was given in the previous part of the problem. So, square root of 9.81 divided by the coefficient of static friction, which is 0.4, and the radius, which is 3.5. This will give us that the minimum angular velocity should be 2.6 radians per second. Next, we will compare this to the actual angular velocity. The angular velocity will be the change in the angle over the change in time. So, write that down, angle over time. But it gives us 28 revolutions per minute. Well, 28 revolutions where every revolution is 2 pi. Because one revolution is one complete trip around the circle, that is 360 degrees, or 2 pi radians. And divide by time, 1 minute is exactly 60 seconds. And that means the actual angular velocity is 2.9 radians per second. And that means this angular velocity is greater than the minimum required, therefore he will not slide down. On the next question, question number 3, a sample of vegetable oil initially in the liquid state is placed in a freezer that transfers thermal energy from the sample at a constant rate. The graph shows how temperature T of the sample varies with time, lowercase t. The following data is available. It gives us the mass of the sample, the specific latent heat of fusion, and the rate of thermal energy transfer. In part A, it says calculate the thermal energy transferred from the sample during the first 30 minutes. So, to calculate the amount of thermal energy that is transferred, we have to use the power. The amount of thermal energy transferred is the power multiplied by the time. The power is given to be 15 watts. The amount of time is 30 minutes, and every minute is 60 seconds, which means that the total energy transferred would be about 27,000 joules. The next part of this question says, estimate the specific heat capacity of the oil in its liquid state. State an appropriate unit for your answer. We will use the equation. The thermal energy transferred is equal to the mass times specific heat capacity times the change in the temperature. This leads us to the equation for the specific capacity being equal to the heat transferred divided by the mass and the change in temperature. The amount of heat transferred is calculated in the previous part of this question, which is 27,000 joules. The mass of the oil is given as being 0.32 kilograms. Now the change in temperature has to be gotten from the graph. It starts at 290 Kelvin and ends at 250 Kelvin. The change in the temperature is 40 degrees. So, 40 degrees Kelvin. Using your calculators, you should get around 2,100, and the units remain the same, joules, kilograms, and Kelvin. So it's joules per kilogram Kelvin. On the next part of this question, it says, the sample begins to freeze during the thermal energy transfer. Explain in terms of the molecular model of matter why the temperature of the sample remains constant during freezing. So you can explain this in one of two ways. You can either use the concept of intermolecular bonds or intermolecular potential energy. So if you use the concept of intermolecular bonds bonds are formed when changing into a solid. And every time an intermolecular bond is formed, this releases energy. Another way to describe this, and it's an either-or situation, is that the intermolecular potential energy of a solid is lower than the potential energy of a liquid. And because of this, when a liquid turns into a solid, it also releases energy in the form of thermal energy. Finally, even though energy is being removed from the substance, the average random kinetic energy remains constant. And this average random kinetic energy is proportional to the temperature. Therefore, the temperature is also constant. In part C of this question, the question asks you to calculate the mass of the oil that remains unfrozen after 60 minutes. In order to calculate the amount of energy needed to change the phase of a substance, we use Q, heat, is equal to the mass of the substance multiplied by the latent heat, in this case specifically latent heat of fusion. So after 60 minutes, the amount of heat removed will be the power times the time, which is 15 watts, times 60 minutes would be 3,600 seconds. Now, this mass that we're talking about is the amount of mass that went from a liquid to a solid state. So it's the amount of mass that froze times latent heat of fusion, according to the question, is 130 kilojoules. But let's just use 130,000 joules instead. Therefore, the mass of oil that freezes is 0.21 kilograms. Now, this is not the answer. Remember, they asked for the oil that remains unfrozen. So the amount of mass of the oil that is unfrozen will equal to the total mass minus the mass that it is frozen, which is 0.32 kilograms minus 0.21 kilograms that froze, which is 0.11 kilograms of oil. In the following question, question number 4, the question reads that there are two loudspeakers A and B, which are driven in phase with the same amplitude at a frequency of 850 Hertz. Point P is located 22.5 meters from A and 24.3 meters from B. The speed of sound is 340 meters per second. Part A, deduce that the minimum intensity of sound is heard at P. Before we start, we have to deduce that if you hear a minimum intensity, it is caused by destructive interference. And because of that, in order for destructive interference to occur, the path difference must equal to some integer m plus 1/2 lambda, which is the wavelength. This is the destructive interference condition. Before we start this, we should probably get the path difference, which is going to be 24 meters minus the 22.5 meters. Which should give you about 1.8 meters. Next, we have to check if this is true, and for that we need to know the wavelength. The wavelength would be the velocity divided by the frequency, which is 340 meters per second divided by a frequency of 850 hertz. And that yields a wavelength of 0.4 meters. So we have m plus 1/2. Let's divide both sides by the wavelength, which is 0.4. And you get about 4.5 wavelengths. And this satisfies the condition. The condition was that the number of wavelengths, which is 4.5, has to be some integer plus 1/2. So it's exactly half a wavelength out of phase, or pi radians out of phase, which means it would be, of course, satisfying the destructive interference condition, which also means there would be a minimum intensity there. In part B of this question, the question reads, a microphone moves along the line P to Q. PQ is normal to the line midway between the loudspeakers. The intensity of sound is detected by the microphone. Predict the variation of detected intensity as the microphone moves from P to Q. So our first statement would be, of course, at P, we already know this was a minimum intensity, because it was at destructive interference, and the path difference was 4.5 times the wavelength. What about at Q? At Q, they're exactly the same distance from A and B. So here the path difference would be 0 wavelengths. And instead of being destructive, this means this is a constructive interference point. And it's a loud or higher intensity point. So what will happen is every time when that the path difference is integer multiple, you have constructive interference. So they have 1, 2, 3, 4. These 4 points, you will have 1 lambda path difference, 2 lambda path difference, 3 lambda path difference, and 4 lambda path difference. You have 4 points of constructive interference. And halfway between them, let's put this in blue or green. This would be 0.5 wavelengths, destructive, 1.5 wavelengths, destructive, 2.5 wavelengths, 3.5, and then 4.5 is up there. So as you move from P to Q, you start at P. It's a minimum intensity. You will cross 4 points of maximum intensity that alternate. And it will alternate between maximum and minimum intensity 4 times, because there's 4 constructive interference points and 4 destructive interference points between P and Q. Finally, at Q, again, it will be constructing interference points. There's a maximum intensity. And finally, the distances between all the constructive interference points and all these destructive interference points are going to be fairly constant. It's going to be fairly constant. So they're evenly spaced. Part C. When both loudspeakers are operating, the intensity of the sound received at Q is I0. Loudspeaker B is now disconnected. Loudspeaker A continues to emit sound with unchanged amplitude and frequency. The intensity of sound recorded at Q changes to I sub A. Estimate the intensity of I sub A over the intensity of I0. At I0, you have two sources which are constructively interfering. Which means that the amplitude of the wave here is 2 times the amplitude of a single wave. When you turn one of them off, you will only get the amplitude A because it's a single wave. Now, combined with the fact that the intensity is proportional to the amplitude squared, this I0 will be 4 times the intensity compared to IA. That means this is 1 over 4. Part D. In another experiment, loudspeaker A is stationary and emits sound with a frequency of 850 Hz. The microphone is moving directly away from the loudspeaker with a constant speed V. The frequency of sound recorded by this microphone is 445 Hz. Part 1. Explain why the frequency recorded by the microphone is lower than the frequency emitted by the loudspeaker. Of course, this is due to the Doppler effect. And in this case, it's the moving observer. This is caused by the moving observer because the source is not moving. And the observer is moving away from the speaker. Now, what is the consequence of this is that the observer is also moving away from the wave fronts coming towards it. So, and this causes the time between wave fronts to increase, which increases the period. The actual wavelength of the waves is unchanged because it's not the source that is moving. The difference is that the observer is moving away. It takes longer for the wavefronts to reach. So let's write that down. The wavelength is unchanged. Finally, the frequency is equal to 1 over the period. Increasing the period decreases the frequency. Roman numeral 2, it says calculate the velocity of the observer. If you look at the physics booklet, you have an equation for the new frequency, which is equal to the original frequency. But now, if it's a moving observer, you have to use v, the speed of the wave, minus u, or, well, actually, the physics book says plus or minus, so we use that one first. The speed of the observer divided by the speed of the wave again. So you have to differentiate the v that they're talking about here and the v in the physics booklet. They're not the same thing. Now, the observer is moving away, so that's how we know it should be a negative sign, because the frequency has to go down, and the only way to have a lower frequency is if you subtract the speed of the observer. If you put in the numbers, the new frequency is 845 hertz. The original frequency is 850 hertz. The speed of the wave is 340 meters per second. And there's only one unknown in this equation, which means you can find that the speed of the observer will be 2.00 meters per second. Question number 5. The graph shows how current I varies with the potential difference V across component X. Outline why component X is considered non-ohmic. It's a one-point question, so it should be just one sentence, something very simple. And very simply, the current is not proportional to the voltage. Another way to say this is you can also state that it's non-linear, or you can also refer to the resistance. Since the slope changes, the resistance is not constant. Part B of this question says, component X and a cell of negligible internal resistance are placed in a circuit. A variable resistor R is connected in series with component X. The ammeter reads 20 milliamperes. Determine the resistance of the variable resistor. So you're given the current, and there's two ways to solve this problem. If you're given the current, you can find the total resistance. The total resistance would be simply the total voltage divided by the total current. In this case, the voltage is 4 volts and the current is 0.02 amperes, which means the total resistance is 200 ohms. This total resistance will be equal to the variable resistance plus the resistance of component X. Finally, all we have to do is we have to find the resistance of component X, and we do this by using the graph. So if you go back to the graph, we know that the current going through it is 20 milliamperes. So let's draw a horizontal line going through that. Where it intersects, it gives us the exact voltage across that resistor. In this case, 2.3 volts. So, the resistance of resistor X would be, again, the voltage across resistor X, which is 2.3 volts, divided by the current of 20 milliamperes, which is 0.02 amperes. And this means the resistance across resistor X would be 115 ohms. Using this in here, gets the total resistance 200 ohms equal to the resistance of the variable resistor plus 115. The variable resistor should be 85 ohms. So this is one way to solve this problem. A second way to solve this problem is you can use the fact that the voltage drop across the variable resistor plus the voltage drop across resistor X would be equal to 4. So the total EMF is equal to the voltage drop across the variable resistor plus the voltage drop across resistor X. Then the total voltage drop should be 4 volts. Now, again, we would use the graph to find the voltage drop across resistor X. We already did that. It was 2.3 volts. Therefore, the voltage drop across the variable resistor would be 1.7 volts. We have the voltage, we have the current, which is 0.02 amperes. The resistance of the variable resistor, actually we changed these here. This used to be for variable resistor, will be equal to the voltage of 1.7 divided by the current, 0.02, which is still 85 ohms. Then, Roman numeral 2, the question asks you to calculate the power dissipated in the circuit. Notice that if it says in the circuit, it's the total power. And if you want the total power, you have to use the total voltage. So let's use the equation for power. Power is equal to the voltage total times the current total, which is 4 volts times 0.02 amperes, which is 0.08 watts. In part C of this question, component X and the cell are now placed in a potential divider circuit. State the range of current that the ammeter can measure as the slider S of the potential divider is moved from Q to P. So first things first, in a potential divider circuit, now you have a parallel path. So if you redraw this, let's draw the source of EMF. You have one path here. It's almost as if you had one parallel path here, and it connects like this. So this resistor represents this one. So, and what happens is these two resistances, call this R1 and R2, they're going to change. So you can make R1 bigger or R2 bigger depending on where you are in the slide. Regardless of what happens like that, the voltage drop in this part, V1, and the voltage drop in this part, in the parallel side, will add up to the total voltage. And the voltage is proportional to the resistance. So if R1 is bigger, it has a bigger proportion of the 4 volts. If R1 is smaller, it has a smaller proportion or smaller fraction. So if you cut it and you start at Q, this part of the resistor will have 0 resistance, which means it has 0 voltage. So the range of voltages starts from 0, and if you go all the way to Q, then this R1 is 0, and all the voltage will be across V2, which means it goes up to 4 volts. But they're asking us for the current range. The current range, well, if you have 0 voltage, the current range will start at 0. And we have to find what is the current when the voltage is 4 volts. So we have to go back to the graph. And we can see that at 4 volts, the current will be 60 milliamperes. So the current range is from 0 to 60 milliamperes. In Roman numeral 2, slider S of the potential divider is positioned so that the ammeter reads 20 milliamperes. Explain without further calculation any difference in the power transferred by the potential divider arrangement over the arrangement in B. So you're comparing a series circuit with a parallel circuit. And in the parallel circuit, only one of these sides has 20 milliamperes, while in this series, the whole thing has 20 milliamperes current. So if we go back to this here, if we can imagine there's 20 milliamperes going through this side of the current, the total current here would be this 20 milliamperes plus whatever current goes through this side. And that means that the total current will be greater. So the total current and the potential divider arrangement must be greater than 20 milliamperes. And this is because some of the current will pass to the other side. Because the total current is greater, it means the total power should also be greater. On this next question, question number 6, the question says, one possible fission reaction of uranium-235 is shown here in the equation, which I will not read. The following data is available. They give you the mass of an atom of uranium-235. You're also given the binding energies per nucleon of each of the 3 elements and isotopes. Part 1 says, what is meant by the binding energy of a nucleus? And the binding energy is defined as the energy required, so energy required to completely separate all the nucleons in the nucleus into its individual constituent parts. So basically, it's how much energy you need to completely separate all the protons and neutrons. Otherwise, you can say that it is the energy released during the formation of the nucleus, which is amounts to the same thing. If it was released when it was made, you have to give it the same amount of energy to separate them again. In Roman numeral number 2, it says outline why quantities such as atomic mass and nuclear binding energy are often expressed in non-SI units. And the basic reason for this is that SI units are often too small to be easily compared. So actually, you should express as the masses and nuclear binding energies. Would the values so the values of masses and binding energies would be too small if you were to use SI units. Next part, Roman numeral 3, it says, show that the energy released in the reaction is 180 mega electron volts. Here's the thing though. You're given the binding energies per nucleon, which is expressed as the binding energy per the number of nucleons there. In order to get the binding energy then, you have to use the binding energy per nucleon and multiply it by the number of nucleons. For instance, if you want to get the binding energy of uranium, you have to use the binding energy of uranium. If you look back up, it would be, actually let's include it here, 7.59 mega electron volts. And you have to multiply this by the number of nucleons, which is 235. The binding energy of xenon is 8.29 multiplied by the number of nucleons in xenon, which is 140. And the binding energy of strontium, SR, is 8.59 times the number of nucleons in strontium, which is 94. The binding energies of the individual neutrons is 0 because they're not bound to anything. And what you have to do here is you have to use the binding energy of the products minus the binding energy of the reactants. So if we calculate these, the binding energy and the products would be xenon plus the binding energy of the strontium minus the binding energy of the uranium. This would give us the change in the energy, how much energy is released. And using these numbers, we get about 184 mega electron volts. Part B, a nuclear power station uses uranium-235 as fuel. Assume that every fission reaction of U-235 gives rise to 180 mega electron volts of energy. Roman numeral 1, estimate in joules per kilogram the specific energy of uranium-235. So, specific energy is the amount of energy per unit mass. And we have the amount of energy that is released, 180 mega electron volts. And the amount of mass is approximately 235 atomic mass units. U. All we have to do now is you have to change the units. 180 mega electron volts would be 180 times 10 to the power 6 for the mega. Electron volts are 1.6 times 10 to the negative 19 joules. Next, what about the mass? Well, it's 235. And 1 atomic mass unit is equal to 1.66 times 10 to the negative 27 kilograms. Using your calculator, you can find that you would get approximately, 7.4 times 10 to the 13 joules for every kilogram of uranium-235. Roman numeral 2 of this question. The power station has a useful power output of 1.2 gigawatts and an efficiency of 36%. Determine the mass of uranium-235 that undergoes fission in 1 day. First, this is the power output. In order to know how much fuel is used, you have to know how much power is going in. So the equation is for the efficiency is the power out divided by the power in. Therefore, the power in is equal to the power out over the efficiency. In this case, 1.2 gigawatts divided by 0.36. That will give us the total power that you need. Now, in order to get the amount of energy, you have to multiply power by time. So I'll just multiply across here and just add the term for time times t times t. And it says in 1 day, so the amount of time is 24 hours times 60 minutes per hour times 60 seconds per minute. Finally, this would be the total amount of energy needed. In order to find the mass, well, let's go back to the definition of specific energy. And I'll use the letter U for specific energy. It's the energy per mass. So if you want to find the amount of mass that is used, you should reorganize this equation. It's the energy divided by the specific energy. So this value here divided by the value that we got previously, which is 7.4 times 10 to the power of 13. In fact, the amount of energy that is released or used in the power station, or that goes in, right, would be 2.9 times 10 to the 14. So it's 2.9 times 10 to the power of 14 divided by 7.4 times 10 to the 13, and you get approximately 3.19 kilograms. This is the amount of uranium that is used every single day. Roman numeral 3, the specific energy of fossil fuels is typically 30 megajoules per kilogram. So just with reference to your answer in part 2, or B1, one advantage of U-235 compared with fossil fuels. So the specific energy of uranium is a lot higher. And what this means, you can get more energy per kilogram. Or you can also state it as you need less fuel for the same amount of energy. Next, in part C, it says a sample of waste produced by the reactor contains 1 kilogram of strontium-94. Strontium-94 is radioactive and undergoes beta minus decay into a daughter nucleate X. The reaction for this decay is given here. Write down the proton number of the nuclide X. And first, you have to balance the equation. The electron has 0 nucleons, but it's a charge of -1. The total charge has to be the same in the left and the right hand side, so it's 38. 39 minus 1 is also 38. So the number of protons is 39. Incidentally, the total number of nucleons is still 94. The graph shows the variation with time of the mass of strontium-94 remaining in the sample. State the half-life of strontium-94. Well, you start with 1 kilogram. That means when you have 0.5 kilograms, the amount of time that has to pass in order to get half the mass would be the half-life. It would be 75 seconds. Part 3, calculate the mass of strontium-94 remaining in the sample after 10 minutes. And we can use two equations. The simpler equation is just the amount remaining is equal to the initial amount times 1/2 to the power of time over the half-life. In this case, the initial amount is 1 kilogram times 1/2 to the power of time is in seconds, because the half-life is in seconds. So it'll be 600 seconds divided by the half-life of 75. And you should get approximately 3.9 times 10 to the -3 kilograms. But if you prefer to use a higher level equation, the amount remaining is the initial amount. The only difference is the base, e to the power of negative, decay constant times time. This is the same result. They will give you the same result. There's just one additional step. You have to calculate the decay constant using the natural log of 2 divided by the half-life of 75 seconds, which is equal to 9.24 times 10 to the -3. You substitute this value into here. So 1 kilogram times e to the power of negative 9.24 times 10 to the -3 multiplied by the time, 600 seconds. This is still equal to 3.9 times 10 to the -3 kilograms. Question number 7. A vertical solid cylinder of uniform cross-sectional area A floats in water. The cylinder is partially submerged. When the cylinder floats at rest, a mark is aligned with the water. So this mark is this mark here. The cylinder is pushed vertically downwards so that the mark is a distance of x below the water surface. At time t equals 0, the cylinder is released. The resultant vertical force on the cylinder is related by the displacement x of the mark by this equation here, where rho is the density of the water. So rho looks like a p, it's just a Greek letter though. Outline why the cylinder performs simple harmonic motion when released. Well, there's one requirement for simple harmonic motion, which is that the restoring force is proportional to the displacement. And in the opposite direction. How do we know that it's proportional? it's in the form of F equals negative kx, where the k would be density times the area times the gravitational acceleration. So we put k is equal to rho times a times g. Part B. The mass of the cylinder is 118 kilograms. The cross-section area of the cylinder is 2.29 times 10 to the negative 1 square meters. The density of water is 1.03 times 10 to the third kilograms per meter cubed. Show that the angular frequency of the oscillation of the cylinder is about 4.4 radians per second. Now, this has less to do with the buoyant force and more to do with simple harmonic motion. You have to have this equation memorized, where the angular velocity is equal to the square root of k over m. In this case, we already stated how to find k. The k is just the constants in front of the x. So it was equal to square root of the density times the cross-sectional area times gravitational acceleration divided by the mass, square root. The density is 1.03 times 10 to the third kilograms per cubic meter. Cross-sectional area 2.29 times 10 to the negative 1. Gravitational acceleration 9.81 divided by 118. Using a calculator, you would get this to be about 4.43 radians per second. And always remember that if you have a show that question, like here, you always find the value to one significant figure more than this. So if 4.4 is two significant figures, you have to show the answer to three significant figures. Part C, the cylinder was initially pushed down a distance of 0.25 meters. Determine the maximum kinetic energy of the cylinder. And there's two ways to get this kinetic energy maximum. First, the maximum kinetic energy will also be equal to the maximum potential energy, because they're both equal to the total energy. This is equal to 1/2 spring constant times the amplitude squared. So we could find this as like we did before, or we can use 1/2 mass times angular velocity squared times amplitude squared. This term here, the k, and mass times omega squared are the same value, because omega, or angular velocity, is equal to the square root of k over m. So replacing or substituting with the values, we get 1/2 the mass of 118 kilograms times angular velocity of 4.4. Now here's the thing, you can use 4.4 or 4.43. So if you use 4.4 radians per second and you square this and then multiply by 0.250, also squared, you would get about 71.4 joules. What about if you use 4.43? 4.43 would give you approximately 72.3 joules. And it doesn't really matter which one you use, as long as you correctly substitute it and show which value you have used, you can use either one. Another way to solve this problem, if you decide you want to use k and substitute, it would be 1/2 the density times the cross-sectional area times gravitational acceleration times the amplitude squared. You will still get the same value though. Part 2 for this question says, draw on the axis the graph to show how kinetic energy of the cylinder varies with time during one period of oscillation. Before we draw the graph for kinetic energy, I'd like to draw the graph for the displacement. I'll draw the graph in blue, and it starts at the maximum displacement. In half the period, it goes down to the other side and comes back up in a sinusoidal graph. What about the graph for velocity? If you draw the velocity in red, you start at 0 because the initial velocity is 0. The slope is negative, so you go to the maximum here. It goes back down to 0 here, and half the period, and goes back up. And yeah, this is the sinusoidal graph for the velocity. Finally, what would the graph for the kinetic energy look like? Well, everywhere where the velocity is 0, the kinetic energy should also be 0. Here's the thing, kinetic energy is 1/2 mv squared, which means that even though here the velocity is negative, when you square it, you get a positive value. So when you square a sinusoidal graph, you still get a sinusoidal graph. It looks kind of like this. And then it will do this one more time. Now you have the graph for the kinetic energy. I will erase the graphs for displacement and velocity. And you're left with this. Here, you can see that for kinetic energy, it only has 1/2 the period. And there's no negative side. The kinetic energy is always positive. In the next question, question number 8, the diagram shows the electric field lines of a positively charged conducting sphere of radius r and charge q. Points A and B are located on the same field line. Explain why the electric potential decreases from A to B. So first, there's several ways you can explain this. You can give the equation for electrical potential. Electrical potential is equal to K, the charge, divided by the distance r. In this case, the distance r to A is smaller than the distance to B. Next, if you graph this, it would look something like this. And you'll see that as you move further away from A to B, the potential decreases. So you go to the conclusion. So potential of A is greater than the potential for B. Next, there's other ways to explain this phenomenon. First of all, if you put a positive charge here, it would experience a force to the right. This is the electric force. So, second force, the external force would be the opposite direction. Now, the work done would be equal to this external force multiplied by this distance. So, the force external times the distance from A to B. Final part times the cosine of the angle. In this case, the angle is 180 degrees because these two forces, this force here and the displacement to the right, are in opposite directions. The work done being negative, work is negative, means the energy decreases, and the work is equal to the change in potential over the charge. Having a negative work means that the change in potential is negative, which means the potential is decreasing. Part B, draw on the axis the variation of electric potential V with distance r from the center of the sphere. Well, one more time. Electric potential would be the Coulomb constant times the charge divided by the distance r. So up to the radius, it's just the inverse relationship graph. What happens here? Inside of the conducting sphere, though, the potential is constant. Recall that the electrical potential is the electrical potential energy per unit charge. Inside of the sphere, there are no field lines. The field is equal to 0. The force is 0. If the force is 0, the work done is 0, which means the energy cannot change anymore. If the energy does not change inside, it has the same value. Therefore, the potential also is constant and the same value. Part C, a proton is placed at A and released from rest. The magnitude of the work done by the electric field in moving the proton from A to B is 1.7 times 10 to the negative 16 joules. Point A is at a distance of 5.0 times 10 to the negative 2 meters from the center of the sphere. Point B has a distance of 1.0 times 10 to the negative 1 meters from the center of the sphere. Calculate the electric potential difference between points A and B. So, you want to get electrical potential difference, which is the work done over unit charge. You cannot use the identity we used before, where this Coulomb constant times charge over the distance, because we don't really have a value for the charge yet. So we have to use the definition here. And it does give us the work done. The work done is 1.7 times 10 to the negative 16 joules. So let's put that into the equation. Divided by the charge. And of course, the charge of one proton is simply 1.6 times 10 to the negative 19. Exactly 1e. Using your calculator, you should get approximately 1.1 times 10 to the third volts. In part 2, it asks you to determine the charge of the sphere. In order to determine the charge of the sphere, we have the change in potential. So let's write that down. This will be the final potential minus the initial potential. So it starts at A, so the initial would be the potential at A, and it ends at B, so it will be here. You use the equation KQ over RB, distance to B, minus KQ over the distance to A. What you have to look at here is this should be equal to the change in potential, 1.1 times 10 to the third volts, but recall we said it was decreasing, so it should be a negative value. Now you just have to input the numbers. We will factor out the Coulomb constant, which is 8.99 times 10 to the power of 9 times the charge Q. And we factored out both of the K and Q. 1 divided by the distance to B. Let's just simplify this without the powers of 10, because so it should be 0.1. It's a lot easier to write. Minus 1 over the distance to point A would be 0.05 instead of 5 times 10 to the negative 2, which is equal to negative 1.1 times 10 to the third volts. And if you use this equation, you can easily find that the charge will be equal to 1.2 times 10 to the negative 8 coulombs. Part D, the concept of potential is also used in the concept of gravitational fields, suggests why scientists developed a common terminology to describe different types of fields. Well, even though it's gravitational potential and electric potential are different concepts, they function similarly. What I mean is they're both used to find the potential energy. And if you have the potential difference, you can find the work done. Using the same word highlights the similarities. And it's highlights the similarities of these different fields. Question number 9. The diagram shows an alternating current generator with a rectangular coil rotating at a constant frequency in a uniform magnetic field. Part A says, explain by reference to Faraday's law of induction how electromotive force, or EMF, is induced in the coil. So you have to basically define Faraday's law first. So you say Faraday's law states that the induced EMF will equal the rate of change of magnetic flux linkage. Just to break down why this has to be the definition, the equation is EMF is negative N times change in flux over the change in time. So when you say rate of change, you're stating that it's divided by delta T. There's a change in the magnetic flux, which is delta phi. And the term linkage just means you're multiplying by the number of loops. Finally, when the coil rotates, so the flux changes. In this case, the flux equation would be magnetic field times the area. Both of these don't change, but the angle does change. Sign of the angle. Therefore, flux changes and EMF is induced. In part B of question 9, the graph shows how the generator output voltage V varies with time t. The average, the electrical power produced by the generator is delivered to a consumer some distance away. The average power output of the generator is 8.5 times 10 to the 5 watts. Calculate the root mean square value of the generator output current. So the first thing we're going to do is we're going to take the graph and use it to find the peak voltage as 25 kilovolts. And now that we know that, we know that the average power is equal to the RMS voltage times the RMS current. And the RMS voltage is equal to 1 over the square root of 2 of the peak voltage. Using the values given by the problem, the average power, which is 8.5 times 10 to the 5 watts, is equal to 1 over the square root of 2 times the peak voltage, which is 25,000 volts, times the RMS current. Using a calculator, you can find that the RMS current would be 48 amperes. In the second part of this question, it says that the voltage output from the generator is stepped up before transmission to the consumer. Estimate the factor by which the voltage has to be stepped up in order to reduce power loss in the transmission by a factor of 2.5 times 10 to the 2. So, the equation for power loss is the current squared times the resistance. So, if you want to reduce the power loss by a factor of 2.5 times 10 to the second, you have to add a factor of, let's put in a different color here, 2.5 times 10 to the second. And you do the same thing to the current. The current is going to have some factor in front of it, 1 over x. In this case, x would be the square root of 2.5 times 10 to the second, which is approximately 16. What this means is the current is 16 times smaller and the voltage has to be 16 times higher. So this is to two significant figures. Part 3, the frequency of the generator is doubled with no other changes being made. Draw on the axes the variation with time of the voltage output of the generator. So let's go back up. We double the frequency. And doubling the frequency means you have 1/2 the period. Second, what would happen to the EMF of the generator? The EMF equation would be omega, the angular velocity, times the number of turns, times the magnetic field, times A, the area, times the cosine of omega t. All this means is the peak voltage is proportional to the angular velocity. Doubling the frequency doubles the angular velocity, so it also doubles the maximum EMF. So instead of having a peak of 25 kilovolts, it will have a peak of 50 kilovolts. Next, it's half the period, so one full wave should fit between 0 and 10. Putting that together, let's put some guiding dots. It will look something like this. Question number 10. The de Broglie wavelength lambda of a particle accelerated close to the speed of light is approximately Planck constant times the speed of light divided by the energy, where E is the energy of the particle. A beam of electrons of energy 4.2 times 10 to the 8th electron volts is produced in an accelerator. Part A, show that the wavelength of the electron in the beam is about 3 times 10 to the negative 15 meters. So, want the wavelength, we just use the equation and input the values. Would be approximately, Planck constant is 6.63 times 10 to the negative 34, multiplied by the speed of light, 3 times 10 to the 8th, and divided by the energy, 4.2 times 10 to the 8 electron volts. And you have to convert electron volts to just joules, so you multiply this again by 1.6 times 10 to the negative 19 joules per electron volt. There's a rather simpler way to get this same calculation. If you look in your physics booklets, the value of the Planck constant times the speed of light is always going to be the same. It's not in the constant sections, it's in the unit conversion sections of your physics booklets, and it has a value of 1.24 times 10 to the negative 6, but the units are electron volts, meters. So the reason this is a lot faster is you don't have to multiply these values. You just divide by 4.2 times 10 to the 8th electron volts. Without any conversions, you would get 2.96 times 10 to the negative 15 meters. In part B, the electron beam is used to study the nuclear radius of carbon-12. The beam is directed through the left at a thin sample of carbon-12. A detector is placed at an angle of theta relative to the direction of the incident beam. The graph shows the variation of the intensity of the electrons with theta. There's a minimum intensity for the angle at theta sub 0. So if you're trying to get the nuclear radius, you have to use the single slit diffraction equation. So the single slit diffraction equation given by the physics booklet is theta is equal to lambda over b. But you have to remember that this is an approximation for small angles. At larger angles, it's actually sine of theta equals to lambda over b. Roman numeral 1 says, discuss how the results of the experiment provide evidence for matter waves. First, you're able to see the single slit interference pattern. And the thing about this is only waves are able to form diffraction patterns. Particles are not able to diffract. Normal particles would not form this pattern here. This must have been caused by the fact that electrons also behave as waves. Roman numeral 2, the accepted value for the diameter of carbon-12 nucleus is 4.94 times 10 to the negative 15 meters. Estimate the angle theta 0 at which the minimum of the intensity is formed. So again, we'll use sine of theta 0 is equal to lambda over b, where b will usually be the size of the slit. In this case, it's the nuclear diameter. So the nuclear diameter is 4.94 times 10 to the negative 15. We have calculated the wavelength previously. So it's 2.96 times 10 to the negative 15. And to find the angle, you get the inverse sine of both this. Divide this first, you get 0.599. So the angle is the inverse sine, or the arc sine, of 0.599. If you use radians, you'd get about 0.64 radians. Or if you use degrees, it would be 36.8 degrees. And this is why you should not use the small angular approximation, because that approximation can only be used at angles of less than 0.1 radians. This is a lot bigger than that. You have to use sine theta here. In Roman numeral 3 of this problem, it says outline why electrons with energy approximately 10 to the 7th power electron volts would be unsuitable for the investigation of nuclear radii. First, in our problem, the electrons had a wavelength of 10 to the 8th. At 10 to the 7th, this is approximately 1 order of magnitude lower energy. So the wavelengths are approximately 10 times longer. What happens then? If the wavelengths are too long, you would not be able to observe the diffraction pattern. Recall that sine of the angle to the first minimum should equal to the lambda over the size of the nucleus. If this wavelength is bigger than the size of the nucleus, you get a value bigger than 1, which means you do not get a first minimum within 90 degrees. In part C, experiments with many nuclides suggest that the radius of the nucleus is proportional to a to the power 1/3, or the cubic root of the number of nucleons. Show that the density of the nucleus remains approximately the same for all nuclei. So we are given this relationship, so we should use it to show that the density is the same. First, the volume of the nucleus would be proportional to the radius cubed, but the radius is proportional to the number of nuclei to the power 1/3, which means the volume is proportional to number of nuclei to the 1/3 cubed. They cancel out. So the volume is just proportional to the number of nuclei. And this makes sense. For every proton and nucleon you add, the volume will increase exactly by the same amount. Second part, the mass is also proportional to the number of nucleons. Double the number of nucleons, you would probably double the mass as well, approximately. Density is equal to the mass over the volume, which would be constant if these two relationships are true. So what basically happens is the density of the nucleus is the same regardless of how many nucleons you put in, because all the nucleons are the same density. And the nucleus is also the same density of the nucleons. Another explanation of this would be that if you have water, it has a certain density. Adding more water does not change the density of the water you already have. Same thing with the nucleus. That is all for today. Thank you for watching, and see you next time.